So as we transition into our next talk from NIOSH, I wanted to acknowledge indirect contributions from NIOSH, which is that NIOSH supports an education and research center at UCLA, and to thank Cass Ben-Levy, who's part of that ERC, who's the person who is responsible for getting us the continuing education credit for safety professionals and for industrial hygienists. So if you happen to be someone who's here present and wants to get those and didn't hear the announcement earlier, please make sure you stop by the desk outside and sign up with her so that you can get those continuing education credits. And also please make sure that you do an evaluation at the end of the day before you leave. Likewise, I wanted to thank Tom Hatfield from CSUN, who's the person who set us up with the REHS credits. Okay, so transitioning into Dr. Methner's talk. So this presentation I'm very personally excited about. I think one of the greatest things that NIOSH has done in this area has been to send out this field site team that's worked with industry to do actual measurements in the field. This has been no small undertaking. The technical challenges associated with exposure monitoring of nanomaterials are immense, and they've done just a tremendous job of it. I also wanted to acknowledge, and this ties in with something that Dr. Schulte said, which is that NIOSH has also done a wonderful job of taking the information that they've gathered through their various studies that may be covered individually by CBI constraints and synthesizing that information into general observations and recommendations that have really helped us to define and move past our sort of purgatory of not knowing how to move forward. And so I think for those of you who are safety professionals or industrial hygienists, you'll particularly enjoy this presentation. Thank you.
Thank you. Good morning, everyone. Good morning, or wherever you are in webcast land. Don't know what time it is there. But oftentimes, we at NIOSH, we get questions from general industry to say, we'd like to know what's really going on out there. I mean, obviously there's a difference between a laboratory experiment that occurs on a bench or in a hood, possibly a pilot scale operation, very small quantities. But people really thirst for what's really going on out there. So that's why I'm taking a little bit different approach right now, and I don't want to move out of the camera way here. And basically do a show and tell for you folks out there in the audience and in webcast land. As far as answering that question in a very small, summarized fashion. So the question is, what is going on out there? And when we emphasize out there, we mean in general industry regarding nanotechnology, nanomaterials, processing, handling, development, incorporation into products, so forth and so on. So with that, I'm going to move forward and describe for you the experiences of the field team. Okay, it's kind of hard to read. This is a busy slide, but a little bit of background and purpose. We were tasked initially to conduct some site assessments at different types of facilities that are engaged in either the handling, manufacturing of these engineered nanomaterials. Using some commercially available instrumentation, because right now there are no unique to nano type instruments, meaning it's going to eliminate any influence from any other material and give you just the nano fraction, and actually translate that into what it means as far as an exposure. So here we are trying to estimate the potential, and I emphasize potential for exposure, because right now the way we're approaching it is it's a strategy, but it's not considered an exposure assessment. So let's get that clear from the get-go. We'd like to take apart the process piece by piece and look at it on a task-by-task basis. So using a combination of direct reading instruments, such as particle counters, they can be condensation particle counters, optical particle counters that actually measure airborne mass concentration. And couple that with some filter-based sampling, which traditional industrial hygienists have done for many, many, many years. And look at it and put the whole picture together. So we're using a bunch of different instrumentation and trying to characterize a given process or material on a task-by-task basis. Keep in mind these are range-finding studies by design. We want to look at the big picture and then take it apart piece by piece so that we can identify which part of the process is emitting a material that could pose an exposure. After we've basically conducted our studies, which would consist of personal breathing zones samples that are filter-based, at source, that's what I call at source, or very close to the particular process, meaning somebody's pouring something into a beaker. Is there a possibility that a plume could be emitted from the light, fluffy powder that they're handling? We would sample very close to that to see yes or no, answer that question. Did a release occur? But really, the key is the direct reading instruments and how they're able to be used as sort of sniffers to find out exactly where along the process there is a potential for a release. We often use open-faced air sampling cassettes, and the reason for that, and a lot of questions have been asked, why do you do open-faced versus a respirable fraction? Well, as an initial assessment, we want to see the big picture. We want to see what the aerosol's characteristics are. So we don't want to, from the start, a priori, take out larger fractions of particles because they could become biologically relevant down the road. Again, we want to examine all the tasks that involve these materials. So basically, you're compartmentalizing the process and taking apart piece by piece, and compare these tasks on a relative basis to each other to see which ones are higher or lower than the others. I'm going to step off here so I can see a little bit better to point with the laser pointer. I'm not sure if the folks on the webcast. This way here? Okay, how's that? Okay. An example here is this is an actual worker making carbon nanotubes. They're single-walled carbon nanotubes in an arc reactor. You can see he's got a lot of protective gear on. He's reaching into a reactor, and he's collecting and harvesting that material. And again, this is a filter-based sample looked at under transmission electron microscopy with EDS so that we can identify which material is which. And you can see here there are some fibrous structures here, but for the most part it's a large agglomerate of sooty material containing residual catalyst. So this is raw material coming out of the reactor, and it's showing you that it can, if he was not protected, migrate to the breathing zone. Again, you can see here is an example of my at-source sample as close as I could get to the opening of that reactor, trying to see if there's a plume that comes out, can I capture it? Well, yes, I did capture it. You can see here he's scraping the inside to continue harvesting the material. And here's what we get on the TEM. Again, there are these fibrous structures, but mostly it's catalyst and it's some soot there. So you can get an idea that not everything is going to come out as single fibers. I mean, in a perfect world, that's what they would want. But these are the initial products that are harvested. They are subsequently handled by different treatments to clean them up and produce their final product, which is a single-wall tube. Here again, he's basically another handling or task involved with this process. He's transferring from tray to tray to undergo a baking operation, and you can see that there are no controls here. In fact, they're using a regular household blender to homogenize this material to break up these clumps. They don't want it clumpy. And we collected a sample right near the transfer operation. I'm not sure if you can really see it. It might be in the background. During this operation, you can see that there's a lot of material that comes off. So this stuff is light and fluffy. It does tend to become airborne. And here's what it looks like under TEM. They have a cleanup operation that's really important to them for purity's sake. And you can see he's using a HEPA vacuum to clean the residual of the materials, mostly soot. And there are some unusual but custom fabricated powder transfer devices we have come across. So these are, like I said, show and tell slides. Here he's using that special device that he's fabricated to transfer the material from the trays, the homogenized, the blender, into a weighing flask. And you can see he's protected. He's got a powered air purifying respirator on with a hood. He's got gloves. They're sealed at the wrist. He's got a disposable lab coat. But if he didn't have that on, his personal breathing zone sample showed that there is material migrating from here, which is the beaker, up into this region because he's got a sampler sitting right there. Again, the at-source sample, which is partially obscured, but it's on actually a ring stand behind the beaker. So it's in that real close general vicinity. You can see that there is a lot of material that does come off when they do that operation. Another example of a manufacturer that's making sheet material out of carbon nanotubes for the electronics industry. They also make a yarn that kind of looks like fishing line. And they were very proactive. This is a larger scale manufacturer in realizing that we don't know whether or not the process emits anything, so we're going to be proactive and enclose and ventilate everything. And that's exactly what they did. You can see they've got an elaborate ventilation system. Each of their reactors is enclosed with removable plexiglass panels. The worker wears personal protective gear while he's harvesting the material. And lo and behold, in this particular case, what we see a lot of, if anything, is amorphous carbon soot. So there are no tubular structures coming off of this, even though the entire sheet is made out of carbon nanotubes. So that's another one of those lessons learned, that it's not necessarily what you expect or think is going to happen is going to happen. Another example, this is a smaller scale research operation using a ventilated balance enclosure where she's weighing out carbon nanofibers, a little bit different. And here's some of the field personnel actually collecting particle number concentration measurements in her breathing zone, and that is also a probe. We're not probing her brain, but that's also another direct reading instrument, so we're kind of, unfortunately, swarming around these folks to get some readings while they're doing these tasks. And also, you can see the two tubes that run across her back. Those are the filter-based samples that are in her breathing zone. And lo and behold, even though she's in an enclosure, there is the possibility of material being released. Now, this is actually what I would consider unusual, because not because she's in an enclosure, but because we're seeing singular fibers instead of what we normally see, which you'll see later, or agglomerated, as Paul mentioned, bird's nests. So these are just examples of what's going on. They make a material called a bucky paper, which is similar to what that other company was making, but on a much smaller scale. And if the material is found to be off spec for whatever reason, they reuse it. And they crumble it up, and they'll put it back in a blender, and they'll homogenize it and grind it up and reuse it again in their process. So here's an example of what they would do here. And at the source, so we sampled right there, you can see that there are fibers that come off. So these are, once again, examples of what is going on out there. Coffee bean grinders are very popular these days, not for coffee, but for homogenizing carbon nanotubes and bucky papers. So once again, she would drop that material into there, run it for a few cycles, and at the source, we're seeing again material being released when they open the lid of the grinder. Here's an example of another person pretty well equipped with personal protective equipment, weighing out multi-wall carbon nanotubes on a scale, on a bench top, no ventilation, no enclosure, no nothing. And we're sampling here at the source, and we're also sampling here in his breathing zone. Now here we did a little bit different sampling technique as far as analysis. We used SEM instead of TEM, and lo and behold, we're seeing these kind of structures now entering the breathing zone. Okay. So after he weighs it, here's another example where a potential for a release could occur. He's dumping it into, I'm sorry, wrong button. He's dumping it into a mixing vessel that's a rotary mixer, and we're sampling here at the edge of the rim of the bucket, and lo and behold, we're seeing material going from here and actually cascading over the top, or possibly rebounding off the surface of the liquid, becoming airborne and being captured by these filters. They were concerned also about the possibility of, during a drying process, there would be a release of this material when they bake it and dry it. Once it comes out of that bucket, it's a slurry, and they put them in trays and they weigh them, or they put them in an oven and dry them. So they were concerned that there might be a release to the general lab atmosphere via the exhaust port. So we basically sampled there for an entire 8-hour drying cycle, and we found nothing, which was a good thing. They were somewhat proactive in their response to this material, given the unknown hazard. And they basically implemented a HEPA filtered air shower that workers would go in and out of, and it locks you in until the complete air cycle has completed. It's almost like a blow dryer at a car wash, where you just stand there and you wait 30 to 45 seconds while jets of air blow particulate off of you. So that was a good thing that they did, in addition to outfitting the workers with personal protective equipment. Another example, this is a metal oxide reactor. This is actually one of those positive case studies that I've come across, where we worked with the company on multiple occasions to solve a problem that was identified during an initial assessment that nobody really was aware of. So there is some value in these field assessments. The problem was that oftentimes after a run, the material is then harvested and they've got to clean the reactor, and the problem is there's a buildup of slag and waste material here. Basically, they're faced with a cleaning task, and how they achieve it is by using some really standard Home Depot type tools you can go into your garage and get. A wire brush, some scrapers for removing paint, and the worker actually gloves up, wears some equipment, personal protective equipment, and he's really got to vigorously brush that material. So you can imagine when you're brushing a powder like that, what's going to happen. Basically, we found during the initial assessment that the material was just being dispersed everywhere. Every sample that I took was positive for their materials of interest. So I recommended using a local exhaust ventilation. This is getting to a question that was raised earlier. We can talk about it more. This particular local exhaust ventilation is used in the welding industry. It's a fume extractor. And welders use this where they put it on the workbench as they're welding, and it draws the fume away from them. So this is basically a low-cost, low-tech application for a high-tech operation. These materials are very fluffy, so we felt that if we could possibly fabricate a flange that would encircle this reactor, as the worker is cleaning, it basically corrals, if you will, the material and draws it through the tube. It's running at about 1,000 CFM, cubic feet per minute, through a HEPA filter, and we did look at the exhaust of that unit and we got nothing. So it was being trapped by the HEPA filter. And basically Paul put the data up earlier and showed it was a dramatic reduction, 80 to 95%, either on a mass or particle number concentration basis. Just by using that small little operation, and it's mobile, it's on wheels, you can go from reactor to reactor, which is the beauty of it. So you don't have to necessarily design a very costly exhaust ventilation system. If you take something like this that's available, modify it to suit your needs, we tested it, we evaluated it, and we were very pleased with the results. Here's an example. Here's some visual evidence of the actual filter-based samples. This was when they were creating nickel, and you can see when they used it, the local exhaust ventilation. Now obviously we can't see nanoparticles, but on a gross scale you can see that there's very little to no material. And here's what the actual TEM micrograph looks like. So given it's not perfect, there is some material that does escape, but you know, it's very sparse. Whereas when they didn't use it, look at what happens. This is breathing zone samples. And you can see the material is much larger, and these were all confirmed with EDS for the material of interest, so we had a nice spike for nickel. We knew that's what the particle was when we were doing the cleaning. Another example is a nano aluminum reactor where they've got these cylinders that collect material inside the reactor. They're filtered, then they're shook, or they're reverse pulse jetted to blow the material off the filter and collect it on the bottom by a gravity feed. And it was funny in a funny sense that this was occurring inside a chamber, and this was the only exhaust ventilation duct that I could find that was designed to control releases inside of that operation. So you can kind of do a little quick and dirty math in your head and say, gee, that's an awful small duct to handle a huge volume of air like that. And obviously workers like to really do a good job, and His job was to look inside that reactor, scrape and brush off any residual, and his breathing zone sample was showing this amount of material on the TEM. These are all nano alumina. So you can see that that smaller duct really didn't do much to protect his breathing zone, or for that matter, the entire atmosphere inside of this walk-in chamber, which was about 10 foot square with an 8 foot high ceiling. Another interesting finding, and we find these things on occasion, sonication of just a small vial of material, water with carbon nanotubes inside of it. Many times people would say and dismiss the fact that, you know, there's no way that anything could come out of it. It's in liquid. How could it become released? Well, we were surprised as well when we sampled inside of that chamber that holds the sonicator. The at-source sample showed that, here's that a really nice example of a TEM micrograph showing the bird's nest. So what we think happened was that it's such a vigorous operation, there's so much energy put into this, that you do get some misting of the water. And those droplets will be ejected from the vial. Within the droplets, that's what's contained in it. And we were able to capture that. So imagine that sonicator working, which it normally would, on an open bench top. Now you're basically dosing your laboratory environment with this material. And they could either remain airborne or they could settle out onto a surface and become a potential for dermal contact. This should seem very familiar to a lot of lab researchers, a standard laboratory fume hood where someone is weighing out carbon nanofibers. She's wearing some protection there, and even though they were conducted inside of the hood, the personal breathing zone sample right here indicated that material does become released and could enter either her breathing zone or the rest of the laboratory. This is another interesting finding that you really don't know about until you see it. It just strikes you when you're on site conducting these assessments. She was doing a very nice job of weighing out. She did use gloves. She did wear a Tyvek suit, so she's wearing all the right things. However, something like this happened where the sleeves started to ride up. And we spotted that, and I took a photo of that. And you can see right here the black showing on the wrist is due to the carbon nanofiber she was weighing out. Another finding that was somewhat serendipitous, because I happened to be looking up at the time, and the ductwork was painted white and carbon nanotubes are black. I spotted this dusting, if you will, at different points on the ventilation system, and noticed that that might indicate that there was some kind of leak. And you can see by the plume that it was blowing out instead of being pulled in to the duct. So this was a positively pressured duct that was handling the fume hood that was supposed to contain the carbon nanotubes. And I took a scraping of that and sprinkled it onto a mixed cellulose ester filter and looked at it under TEM, and lo and behold, there are carbon nanotubes. And that was something that could have easily been missed if somebody, for lack of a better word, didn't have a trained eye to look for something like that. So these are things that pop up over and over again. Again, here's somebody involved in wet cutting with a saw, circular saw, nanomaterial composite. So here we have the carbon nanofibers embedded in a plastic composite material. And as Paul mentioned earlier, the thought was, well, once it's bound into a matrix, it's an epoxy, these fibers will not be released. Well, this slide tends to say otherwise. This material here does end up in his breathing zone, potentially, if he was not protected. He's wearing a mask. And you can see that the material is fibrous in structure. We did confirm it with TEM and EDS. And also inside the enclosure, this is just a series of three-sided curtains, plastic vinyl curtains that are supposed to basically keep this stuff from going all over. Obviously, a wet saw is a very dirty operation. So you can see we were sampling inside, and here's what it looks like. And then we were sampling outside to see containment effectiveness, and we're still getting material migrating outside. Surface grinding is another popular task that they do to the composite material. And here's a worker that's involved in using a surface grinder. It's got some local exhaust ventilation right here with a straight takeoff. Keep in mind that the wheel the pattern of the circulation of the wheel is, I believe, left, towards the left. So they put an inlet on this side to try and capture stuff that was spun off of that wheel. And it really didn't do a very good job because, once again, we're getting material up in his breathing zone, even with this local exhaust ventilation. I think the reason is because of the positioning, that it didn't have a dramatic effect on capturing that material, because you're expecting a particle plume that's running horizontal to now turn 90 degrees and go up into a ductwork. And it really doesn't work very well. And the at-source sample, once again, showed that even right over here, and you can see the samplers right above the grinding head, we're getting materials there. There's some interesting applications of local exhaust ventilation. You can see here that this is a relatively standard light fixture on a tensile tension machine that is working with, or it's trying to break some composite material. And they felt like, well, we need some ventilation here, so we cut a hole up in here and we connected a duct to our local exhaust, or our general exhaust system for the laboratory. So I don't know how effective that worked. Here's another example of a wet saw spinning off a plume of carbon nanotube material within a composite. And you can see this nice black striping on the wall behind it. Obviously, there's a need for some type of control here. We don't want to just randomly and grossly contaminate things unnecessarily. Here's another example where the worker himself was doing that wet cutting on a table saw this time. And again, his personal breathing zone and the general area. And here's the general area sample right up on the wall. Here's his breathing zone. We're finding tubular material. Again, he was wearing short sleeve shirts, and there really was no concern about dermal exposure, and lo and behold, it did occur. I also captured a plume, or a droplet from the plume emitted from the blade, and we can see once again the bird's nest. So it's out there. Here's some unique enclosure designs that are coupled with local exhaust ventilation. Here's a paint stirring stick that operates a trap door of some type. I really don't know what this is, but they were capturing something here with an exhaust inlet. Shop rags are really good for altering airflow patterns around a grinding wheel. And here's another one with some good old duct tape on here. So these things are out there. People think they work. They try hard to do their best. Here again, the worker's doing some belt sanding. And again, we see tubular material and then some other particulate that's really not tubular, but it is nanoscale. A lot of these materials come in on pallets. If you're a high volume user, 5-gallon buckets. And this particular operation, they tried using a walk-in ventilated booth to do some transfer operations into graphite boats that they would subsequently heat treat. So they take material from the buckets and then add them to the trays you'll see later. Here's an example of the floor that started out as being white. There's something else in there that might bother you if you were a health and safety professional responsible for this particular operation. You can see that they use a leaf blower to clean up carbon nanotubes, as well as a shop vac. So when things get dusty, they just kind of blow it into the booth and hope that it gets trapped. Here's the actual transfer operation, and here's his breathing zone. Even though he's in a ventilated booth, the material still does tend to migrate towards his breathing zone. Here he's vacuuming up the trays to get residual that had spilled onto the trays. And you can kind of see, I'm not real sure if it's a real good photo, but there's some dark speckling here on his Tyvek suit, and that actually accumulated during that process. So it would have gotten onto his street clothes, if you will, if he wasn't wearing that. Another thing that we do recommend is sticky mats, and they do work, provided that you change them out regularly. Surprisingly, this was only 6 trips in and out of that room, and look at the level of contamination. So to summarize, actually we've increased the number now. I think we've got 31 site visits that we've been completing, or we have completed to date. A variety of nanomaterials have been studied, quantum dots, single and multi-wall carbon nanotubes, different metal oxides. We've seen a variety of controls, as you can see, that have been used with varying degrees of effectiveness, and the different types of personal protective equipment or lack thereof. So we're getting the big picture now, and I think that was important as an initial step in characterizing this industry and what is really going on out there. These tasks, we did find certain tasks, as you can see, were potential contributors to exposure. So that was an important step in identifying them. Emissions and subsequent exposure do occur. Regardless of what people may think, it can happen. What we found is that, as you can see by a lot of those micrographs, electron microscopy is very important, because a lot of times the direct reading instruments don't know a carbon nanotube from a speck of airborne dust. Counts it as one no matter what. The TEM actually allows you to do a little bit better job of characterizing that material, looking at its size, shape, morphology, and chemical composition where applicable. Again, these are initial assessments, but the goal is to identify. So once we identify, we could then come back and do some more detailed studies. As an example was the local exhaust ventilation study that we did, where on the initial assessment we found a release, we came back, we made recommendations. The recommendations were implemented. We followed up with an additional study to measure the effectiveness of that recommendation. So future work, I think that what's really important is we need, and Paul mentioned earlier about the occupational exposure limits, we need to have some numbers put forth that we can compare against. Because right now the standard question is, well, is this harmful? And am I out of compliance? Well, the answer is I don't know and I don't know. So we're moving in that direction. I think it's just time will tell. But we really do need to come up with some numbers to compare against. More detailed personal exposure assessments for, let's say, a full shift would be important down the road as part of a more detailed investigation into these types of studies. At any of these facilities that are identified as having personal exposure. And guidance on validated and field-tested methods and instrumentation is really important. And that's kind of where we're struggling right now, because there are no instruments out there that are nano only and do it all. So we've got to work towards that into the future. And engineering control effectiveness studies are really needed. Once we identify the problem, we make that recommendation, they implement it, we need to find out whether or not it's really working or not. So with that, I think I am out of time, and I'll entertain questions.
Thank you. While visiting all these sites and seeing, the different levels of stringency, is it known that any of the workers actually inadvertently received a high dose? Has any personal exposures?
No, it's really hard to work backwards. And even if you were to question them and say, well, before you ever put on that suit or that respirator, what did you do? And it's hard to estimate what they could have potentially been exposed to. We were just working on that particular day. That's what we saw, and that's what we reported on. And keep in mind too that every one of these sites that collaborate and cooperate with us get a report outlining all of these results. And I didn't overwhelm you today with all the numbers that we collect, because we clearly don't have enough time. But every site gets a report that describes the process, what we did, what we found, what it means, and what our recommendations are. So, for example, like the reactor clean-out, recommended the local exhaust ventilation. They took that, they ran with it, implemented it, we came back and we analyzed it. and see how effective it was, and it was pretty good.
So any of the health surveys in the workers in the areas or the companies that work with nano products, any of the health surveys in these workers in their annual occupational health survey shown any
we didn't look at any health data at all. These were strictly industrial hygiene type survey assessments. So yeah, we didn't go back and say, did your doctor ever, make a comment about, your respiratory system seems to be compromised in some way or another. Nothing like that. So we couldn't put the two and two together. In the future, that may become very important. Medical surveillance coupled with the industrial hygiene assessments. So we can link exposure and possibly health effect. Yes?
Mark, Larry Gibbs from Stanford. Very good information. I just want to understand the context of this, because when you're doing the sampling, you didn't quantify the amount of sample, et cetera, that you were gathering. I assume you have that data somewhere.
Well, yes.
But you were qualitatively looking for whether there was any amount of release. Is that correct?
Yes, sir.
All right. I just wanted to clarify that,
yes,
because it sounds like every time you found something, it wouldn't be unexpected to find something if you don't have total isolation or something else in many cases.
Sure. And to follow up further on that question, we did collect a mass-based sample for the carbonaceous materials, where we use elemental carbon as a rough indicator, surrogate, of the presence of that material, because in the case of carbon nanotubes, they're made up of elemental carbon. So we now have a mass concentration side by side with a TEM analysis. So in addition to the particle number concentration. So we try and put that together as a package.
We have a couple questions from the web while the microphone's moving. What is the current recommendation on disposing HEPA filters and other PPEs trapped with nanomaterial from the NIOSH standpoint, or regular general solid waste?
Well, Paul, you have anything to add to that? Right now, as far as disposal of the material, if you consider it a hazardous waste, obviously then that waste needs to be segregated. But right now, NIOSH does not have any guidance on how to properly, if there is a term for that, dispose of contaminated filtration media. Not to say it's not an important question, but we haven't gotten there yet.
Yes, I just wanted to know, did you make an assessment of the kind of other particles, type particles or fibers that might be present in the atmosphere when there was no nanomaterial going on? Yes. How are you going to correct your data?
Very good question. We refer to those as incidental nanoparticles. Could be on the same scale as the material of interest. Basically, if we're using numbered concentration data via the direct reading instruments, we take a background sample before and after. So we collect data before and after the operation, that particular task. So what we're looking for is a background level that's here, and when he does something, there's a spike that we can attribute to that particular process and assume, because once again, these instruments don't know the nanotube from the speck of dust. They count them as one. And then it comes back down when the task is over. That's another background. So we average the two backgrounds and subtract it from the actual task-based number. So that gives us a rough estimation. It's not perfect.
Mark, you might mention some of the sources of those kind of incidental nanoparticles.
Sure. Things like combustion sources. Anything that has to do with a gas-fired heater, you will have high levels of incidental nanoparticles. Forklift trucks. Any internal combustion engine will put out particulate. Things like photocopiers and printers could do that. So you really have to be careful and really know how best to isolate your particular task. So that's why we collect so much data before and after. We bracket that process as best we can. Follow it up with the filter-based samples to get visual evidence, and the mass-based samples as well. So there's multiple instruments and tools and strategies being implemented for every given sampling effort. And then we put it together. But yeah, there are occasions where you'll see that incidental background sort of drift up a little bit. You could be near a highway, and you can see as rush hour increases, your particle counts go up. Sometimes it might mask a very subtle release. Like I said, it's not a perfect system. But for the most part, we're very successful at identifying tasks that actually do emit materials. Does that answer your question? Well, like I said, we really don't extrapolate that data because it's such short duration samples. Our intent is not to extrapolate it to an 8-hour work shift because it is so intermittent. And there might be other sources of exposure that we are not accounting for that could contribute to a load on a sample. So, like I said, as an initial assessment, we want to identify first what's released, if anything. And we can come back and do a more detailed assessment. And we've only done them on a handful of these site visits.
Great. What is NIOSH's recommendation on clean contamination areas with nanomaterials? Is the cleanup of this contamination considered as part of HAZWOPER with all of the uncertain risk data we have now?
That's another very good question. I don't personally have an answer for that. Obviously, an unknown, uncharacterized material should be treated carefully. So we would want to minimize any type of dust resuspension if it is a dusty material. So things like wet cleanup and HEPA filtration would be prudent until we get a better idea of what concentrations are either unacceptable or acceptable. So yeah, again, we're in our infancy right now as far as just characterizing the industry, and we're taking it step by step, and we're working towards answering that question. We just haven't gotten there yet.
Hi, Mark. You had mentioned, there was a question about the effectiveness of ventilation systems, and you showed us that with the HEPA filter, the local HEPA filter that you tested, that it showed that the exhaust, it was cleaning up pretty well. Do you have any data on, like traditional systems, like baghouse systems and whatnot, on local ventilation?
No, not at this point. Like I said, that was sort of an opportunity that presented itself, and I kind of seized it and said, well, let's try something that's relatively low cost, commercially available, easily implementable, and let's see if it works, because that work had not been done yet. So we were trying to basically not hit the wallet of the company too hard as a starting point, and just happened to get lucky, and it worked better than we thought. So that just, I'm hoping that that kind of work will springboard into more studies that will then look at, as you said, bag houses, other more sophisticated exhaust systems that you can prove with data that they work.
Thanks.
For the worker weighing nanomaterials in the fume hood, since particles were not effectively captured, do you recommend other controls beyond the fume hood while weighing materials? And the sort of follow-up is, were the releases due to inadequate engineering controls or sloppy work practices, or both?
Yeah, the answer is probably both. That is a very sloppy job. It's very manually oriented, where you've got to weigh out a certain amount, and you're scooping things. Personally, I would like to see an automated powder transfer system that you would never have to even touch the stuff. But that's really not appropriate for that kind of an environment. What I did notice was that the sash was up very high because they needed to reach, so they would tend to raise it. That would in turn drop down your face velocity and your control of the material. But there's been other work by Mike Ellenbecker out at UMass Lowell with Canvas Sci, and they've shown that materials, because of turbulence inside of the laboratory fume hood, the probability of material being ejected back is pretty good. They've measured stuff outside of the hood, even though they had the sash at a working height. So that sort of confirms what I found, or I confirm what they found, either way. So that type of an operation, maybe something along the lines of a ventilated glove box might be appropriate. But we're still working on all of these different recommendations for engineering controls because there's so many out there and we haven't tested them all. So these are, once again, they're intended to seed some thought into some future research on what works and what doesn't, and we're working towards that. We've seen them out there. Oh, I'm sorry. We've seen them out there in varying degrees. Oh, I'm sorry. Maybe you need to repeat it.
My question was, for the people who are online who couldn't hear me, was what about biosafety cabinets that are used in the pharmaceutical industry, specifically that have been designed for transfer powders? Are those perhaps more effective than the chemical fume hoods?
They could be. But what we've seen as sort of a trend is that a lot of these companies are very small. They're startup type companies with not a lot of spendable cash, if you will. And so they're going to opt for something that's the most reasonably priced, yet still effective. And we're still trying to weigh that and say, well, I recommend, let's say, a biosafety cabinet, but they would say, well, do I really need that? I'm only handling 100 grams a day. Maybe a low-flow ventilated balance enclosure would work just fine. So you see, we've got to gauge that. You know, at what point do we walk that line and say, this is acceptable and this is not? That's where, you know, especially occupational exposure limits, those types of numbers could come in very handy to serve as a comparison point for what works and what doesn't. Can we stay consistently below a magic number, if you will?
Mark, did you find any situations where their nanoparticulate was escaping from a colloidal solution?
Not so much colloidal, but the sonication in just regular water with organic material. It was an environmental lab, so they were looking at natural organic matter in water that contained carbon nanotubes. The material did become airborne as part of that aerosol droplet complex. So once that water evaporated, two things could possibly happen. It remains buoyant in the air, or it settles onto a surface and becomes available for incidental contact on, let's say, a lab bench or a chair arm or something like that. So it did come out. The recommendation there would be to put it inside of a ventilated structure like a laboratory fume hood, turn it on, close the sash, and then you come back when it's done sonicating. See, a simple, effective control strategy like that could work very well. Another question.
One last question from
Mark, I just had a quick question about, you folks are still trying to secure additional site assessments.
Absolutely.
In the interest of that, I was wondering if you could speak briefly to the concerns folks might have about confidential business information and so on and so forth. Maybe share a little bit about what happens to the data afterwards.
Okay. Well, what NIOSH has been doing for the last probably 5.5, 6 years now is a company would doesn't have to be a company, it could be another government agency for that matter. Somebody is engaged in nanomaterial handling, production, use, incorporation into a product, and they would call us and say, we would like to have an initial assessment done by the field team. And that's where we spring into action, and we schedule something like that after, you know, talking to the folks on the phone, maybe doing an initial walkthrough survey, just observational to see what's going on. We would come back and we would do a sampling effort like this that generates data like that, so that we can look at their process from start to finish and categorize things based on their potential for releases, which could in turn result in an exposure. Once that's done, we would then analyze data, look at the filters by TEM, and sort of put together a report that's roughly like a journal article where, you know, you've got your background information, your materials and methods, results, discussion, and conclusions. And we would give that back to the company or the requester as sort of, it's a free service. To say, you know, we appreciate you inviting us in to conduct our research, and here is what you get in return. That they can then use to say, oh, I didn't know that sonication resulted in a potential exposure of my laboratory workers. Thanks for the recommendation. I will implement that, and we could possibly come back and sample again and say, yes or no, did it or did it not work? Based on that, any information that's in those reports, if it was to be used as part of, let's say, a support for a journal article, is de-identified. And confidential business information is maintained. These are basically internal reports within NIOSH that you as the requester and NIOSH are the only ones that have copies of that. So we do maintain confidential business information and proprietary information. And there have been occasions where a company just says, well, I really can't describe that process to you. It's strictly proprietary, and nobody aside from those that maintain that intellectual property are allowed to even hear about it. So it has gone to that point, but for the most part, companies they're wonderful, they're cooperative, they're collaborative. They really want it. It's been a good experience overall. So that's what they have to look forward to when they contact NIOSH and say, I'd like to have a site assessment done.